Destroy shit, pinpoint asteroids in orbit, then hurl y'all thousands of miles an hour towards it.
What's up, Earthlings? For centuries, mariners navigating the oceans in the northern hemisphere have used the North Star, also known as Polaris, to determine their latitude. For any point between the equator and the North Pole, latitude is figured out simply by measuring the altitude of Polaris. For example, at 30 degrees north, Polaris can be seen 30 degrees above the horizon. The relationship between latitudinal position and the apparent altitude of Polaris is due not only to the star's distance and location over the North Pole, but also to the Earth's spherical shape. Astronomers have determined that Polaris is 433.8 light years from Earth. This extreme distance has two important effects. First, it's the reason why the stars seem to be stationary, directly above the North Pole all year round, despite the Earth's annual orbit around the Sun. And second, light rays from Polaris are virtually parallel when they reach the Earth. This means that all the light from Polaris meets the Earth at a 90-degree angle. The vast distance of Polaris is not an arbitrary assumption. It literally has to be very far away in order to produce the angles at which it is observed from Earth, with respect to the Earth's equatorial plane. Flat Earthers will often protest that it's impossible for Polaris to appear always above the North Pole, considering that Earth is traveling around the Sun at an orbital path at 940 million kilometers in circumference. This argument is irrelevant with respect to the shape of the Earth, and is merely a bad argument for a stationary Earth. Nonetheless, flat Earthers simply lack understanding of the geometry of the heliocentric model. The distance the Earth travels during its annual orbit is minuscule compared to the distance of Polaris. Consider this. The diameter of Earth's orbit around the Sun is about 186 million miles. The distance to Polaris is about 2.4 quadrillion miles. That's a distance ratio of 1 to 12 million. Since Polaris is very distant, the angular shift over the distance from our North Pole to the equator is imperceptible and can be ignored. To put this into perspective, imagine you're staring straight ahead at a distant mountain located 100 miles away. Now take a step 8 millimeters to the left. Obviously, you're still staring at the same mountain. If you are the Earth and the mountain is Polaris, that 8 millimeter distance is the equivalent of the change in Earth's relative position after 6 months of orbit. The exact distance of Polaris is not what's important in this discussion. What matters is that it's far enough away that its rays are parallel, that all its light comes in at the same angle. The result of this position of Polaris in relation to the Earth, its location, and its parallel rays is that the apparent altitude of Polaris above the horizon is determined solely by the curvature of the Earth. An observer at the North Pole will see Polaris 90 degrees directly overhead. The location of the North Pole is latitude north 90 degrees. At the equator, an observer will see Polaris 0 degrees on the horizon. The equator is located latitude 0 degrees. To a sailor or traveler in the northern hemisphere moving directly south, for every 1 degree of latitude traveled, Polaris will appear 1 degree lower in the sky. The altitude of Polaris is therefore always equal to an observer's latitude. The angles at which we observe Polaris from any location in the northern hemisphere match perfectly with the geometry of a spherical Earth. All of the methods and formulas used in celestial navigation employ the geometry of a spherical Earth. The fact that they work is no mere coincidence. In fact, if the Earth was flat, the methods would not work at all. The geometry of a flat Earth is very different and would require different methods. For example, the congruous relationship between the altitude of Polaris and the latitude of the Earth is impossible on a flat Earth. To a traveler on a flat Earth who is moving away from Polaris directly south, the apparent altitude of the star will decline, but not at a constant rate as would be seen on a globe. In fact, the farther away an observer gets, the slower Polaris will appear to descend. It's a matter of simple geometry. As the degree of altitude decreases, concurrent distances increase. This means that the altitude of Polaris will almost never agree with an observer's latitude. To see Polaris at an altitude of 0 degrees on the horizon, as observed at the equator, would actually be impossible, because an observer would have to be an infinite distance away. Basic trigonometry reveals why. You can verify this for yourself. In this illustration, which is drawn to scale, you can see that Polaris, if positioned at a height of 3,100 miles above a flat Earth, will have the correct matching altitude from 45 degrees north latitude, but not from anywhere else except the North Pole. Where is Polaris on a flat Earth? This illustration shows why the altitude of Polaris cannot match an observer's latitude on a flat Earth. There is no way to reconcile this inconsistency of the flat Earth model with observable reality. The apparent position of Polaris in the sky, as observed from any location in the northern hemisphere, indicates beyond the question the curved shape of the Earth. This is empirical evidence that anybody can validate for themselves by simply measuring the altitude of Polaris with a homemade clinometer and comparing that result with their latitude. There is no theoretical distance above a flat Earth where Polaris could be positioned that can mimic this relationship. It's impossible. The simple fact is, angles on some fixed point behave differently with distance on a curved surface versus angles on a flat surface. A plane just can't mimic a curve. The sun also reveals the shape of the Earth. It's not just Polaris that doesn't work on a flat Earth model. None of the celestial objects above a flat Earth would appear where they do in reality, including the sun. The sun would never actually set on a flat Earth or even appear close to setting. The Earth is way too small. Here's why. Like Polaris, the sun is far enough away that its rays are virtually parallel when they reach the Earth. During equinox, the sun is positioned directly over the equator. Therefore, the sun's angle of altitude will be 90 degrees at the equator and 0 degrees at the poles. On a flat Earth, where the sun supposedly sets due to perspective, as the sun's angle of elevation decreases, concurrent distances increase exponentially. With regard to latitudinal position, this means that an observer's latitude will always be equal to the sun's angle as measured from 90 degrees overhead. To see the sun at 10 degrees above the horizon, an observer would have to be over 17,000 miles away. To see it 5 degrees above the horizon, he would have to be over 34,000 miles away. To see the sun 1 degree above the horizon, an observer would have to be 172,000 miles away. This is why the sun would never set on a flat Earth. So far, not one flat earther has been able to resolve these problems with the flat Earth model, or should I say, their lack thereof. But that doesn't stop the community from trying, or in some cases, not trying at all. I want to give a special shout out to my boy Seek Truth, Speak Truth, who, in my words, is a perfect example of someone finally being honest with themselves. Again, thanks for watching. Don't forget to like, share, and subscribe, and I'll see y'all on the next one. Peace.
Destroy shit, pinpoint asteroids in orbit, then hurl y'all thousands of miles an hour towards it.